Hi, I'm Professor Sri Narasimhan of the Scheller College of Business at Georgia Tech. I'm teaching this course on data analytics in business. This module is on variable selection and regularization. We have 6 lessons in this module: the introduction to this topic, the best subset selection procedure, stepwise selection, choosing the optimal model, ridge regression, and lasso. So, we are going to see why this particular problem is important. So, variable selection and regularization are becoming important thanks to the fact that advances in IT lend us the ability to capture large volumes of data. We now have several domains where each observation of a subject or an object has hundreds if not thousands of attributes. For example, in business applications and settings, we could merge databases from multiple sources, resulting in a plethora of attributes for an observation. Or if you think of your healthcare record, you have hundreds of attributes about you as an individual. So, a critical problem is to determine which attributes are most relevant for decision makers. This is especially true in business settings. So, in this module, we will study approaches that help with this problem of selecting variables and this idea of regularization. So, we can then use our models that we have developed for prediction, which is a very common application of analytics and data science in general. In our module on linear regression, we have seen how the least squares estimators are obtained. They are obtained by trying to minimize the sum of squares in the regression model. For the purpose of this lesson, please note I may be using the terms model or method interchangeably. So, sum of squares error is given by that formula that we have seen in the earlier module on linear regression, and mean squared error is the average of those values. Note that y hat is also written as f hat and is the predicted value for the ith observation, which we get from this relationship between y and x. While ordinary least squares tries to minimize sum of squares error on the training data, we are very often interested in how the estimated model performs on the test data, especially in prediction. So, we want to find a method or model that gives the lowest test mean square error as opposed to training mean square error. Note that there is no guarantee that a model with the best training MSE will also have the best test MSE. There are other terms that we are interested in this context. We are going to talk about variance and bias as it pertains to a model in the context of predictions. Variance of a model refers to the amount by which the estimated model would change if we estimated it using a different set of observations in the training data. If a method has high variance, then small changes in the training data would yield large changes in the model or in the parameters of the model. Generally, more flexible models have higher variance since they tend to follow the training data very, very closely. Bias, on the other hand, is the error that is introduced by approximating a complicated real life problem with a simpler model. For example, using a linear model to model a true nonlinear relationship. So, in fitting models for prediction, one has to consider the trade-off between variance and bias. So, at any point x0 in the test data, we can compute this particular term, expected test mean square error, which is the sum of the variance, the square bias, and the irreducible variance of the error terms. We do not need to know the proof for this in the course. So, this expression on the has variance plus bias squared plus the irreducible variance of the error term on the right hand side, and the expected test MSE is shown on the left hand side. So, the left hand side refers to that expected test MSE. The overall test expected test MSE is calculated by computing the average value of that expression over all the test points in the test data. The challenge for modelers is to find a method for which both variance and squared bias are low. So, we are interested in models that have a good prediction accuracy. So, we know that in linear regression that is the model that we have, and we are typically fitted with least squares to get estimates of the betas. So, we want to develop alternative ways of fitting to get better prediction accuracy and also interpretability of the model. If the relationship between y and x is linear, then least squares estimates have low bias. Also, if the number of observations is bigger, way bigger than the number of predictors, then ordinary least squares will generally have low variance as well, and it will perform well on test data. If n is not much larger than p, then there can be variability in the least squares fit, resulting in overfitting and poor predictions on test data. Note that if the number of predictors is greater than the number of observations, then the least squares method cannot be used. So, in regression, what we can do with the regression model is we can constrain or shrink the estimated coefficients so as to reduce variance while not increasing bias significantly. This approach can improve accuracy of predictions on test data. In a lot of scenarios, many of the variables used in multiple regressions are not relevant. So, if we can remove these variables, we can get a model that is better and more suitable for interpretation. So, approaches to remove these non-relevant variables are called feature selection or variable selection. So, there are alternatives to using least squares include subset selection, which we are going to see. So, this involves finding a subset of the p predictors that are best connected or related to the y variable. We then use this subset of variables in least squares regression to fit a model. Shrinkage or regularization. We fit a model with all p predictor variables, but then shrink the coefficients to nearly 0 compared to least squares value. By doing this, variance is reduced. If lasso is used, then some coefficients move to 0, which leads to variable selection. Finally, there is dimension reduction, which we will not study in this course, but that basically involves finding m linear combinations of the predictors and then fit a linear regression on these m new variables. So, in this introduction, we had a quick look at why we need techniques to deal with large number of predictors in some applications. We also had a very quick look at the bias variance trade-off when using a model, let us say ordinary least squares for prediction.